like that. And then, so the pink is say a tertiary, and then the white is a primary. Right? Mix that up. Here's primary, and white is tertiary. Okay. Best example, right? Just between two of them. I can draw another one in. The secondary would be between the primary and the tertiary. Okay, so what that means is if you go according to a tertiary, forming a tertiary radical, you go through a smaller hill as opposed to a primary, which is a bigger hill. Now between a bigger hill and a smaller hill, since we're all lazy here, myself included, which one would you rather go through? Tertiary or primary? Tertiary, right? And so chemistry is very lazy, and it always wants to go through the lowest energy pathway, which is always a tertiary, which is why we favor a tertiary carbon radical over a primary. Okay? Now, for bromination, it's endothermic. So we start off here, and we end up at some higher energy state, right? So I would draw it like this. Okay? And then for the pink one, something like that, right? Same thing. Now the difference is between fluorination and bromination is that for bromination, this activation energy is closest to products. And that's what the Hamming postulate is. Alright? And so the Hamming postulate is saying that the energy of the transition state will either be more similar to the products or reactants. Okay? And so when the reaction is endothermic, the transition state will be more closely associated with the product than in an exothermic reaction where the transition state here is more closely associated with the starting material. So now we have to refer to why it's more selective, okay? So let's just start here, right? And so let's just say you're starting the reaction and you're starting a marathon, right? And when you start a marathon, you're highly motivated and you're not stressed out, you're not tired yet, right? So between going up hill A or B, even though one is higher, you're still not that, you're not tired yet. So you're not going to be as selective, right? You can go over the big one or small one, not really that big of a deal. But if you're running a marathon and it's been like, say, you're running for 5 hours, right? And you get to here. Now that difference, even though it's about the same, you want to go to the lower energy pathway because you've already wasted so much energy, going up this hill and you're just really tired, stressed out, you just want to go to the lower one, which makes this more selective. All right, is everyone at that? That's my metaphor. So
the pink is still the primary, correct?
yeah, pink one's primary. Bromination, it's more selective because
exactly, you're more selective. You're tired.
yeah, because you're retired and So look at the energy gap, right? Between here and here, it's small, right? Between here and here, it's really big. So you basically want to go to the lower energy pattern once you get to right here. So that's makes sense. Like from here, this isn't that much of a difference starting out. Questions so far? Not too bad, right? Okay, so part D. Alright, so for part D, before I start, I just want to tell you that whether you put the VR2 like the way I have it on the paper or like this, it doesn't make a difference, right? As long as it's clear cut and easy to recognize what you're trying to do, you don't have to put it in a certain way. As long as you know that this molecule is reacting with VR2 through a bromination reaction to get the product, right? And so for part D, it asks you to give 4 more possible products, right? And I'm going to give you 5 more, all right? So this is one. Another one would be bromination here or here, right? So I'll go here on top. Okay? But if you think about what's happening in the reaction, going back to the propagation steps, right? The intermediate for this is you pluck off a hydrogen from that primary position, right? From a radical. So for this is put A, B, C. You form that radical, right? But next to a pi bond, it's an allylic radical, right? What's the name? So you form an allylic radical, which means there's resonance, right? And so what happens is that this electron and then one of the electrons from the other pi bond, like that, right, will form a new pi bond, and then the remaining electron in that pi bond goes to that carbon. You get that? From a radical, right? Which means this radical can react with bromine. So, besides just A, right, you also get that. Now let's look at molecule B. So since you're replacing the hydrogen down here with a bromine, that means that you're going to have to form a radical here. Okay, and taking out one of the hydrogens here. Form a radical. That's A, B. All right. So same thing. You get resonance. Right? Radical here, one electron from that pi bond, from a new pi bond. The electron from the existing pi bond is broken, the remaining electron goes to that carbon. Right? So you end up with this. Right? So from there, you form a tertiary radical, and then it's going to react with VR2 again as one of the propagation steps or termination step. You end up with this. Alright? Now let's look at C. What's C? So between C, I plug up hydrogen from the top. happens, you form you have a resonance. So, the electron, one of the electrons is going to form a new pi bond with that radical, and then the remaining electron in that pi bond simply goes back